alkali metals. Halides of alkali metals. All forms means all the member. All forms halides of type MX means lithium, sodium, potassium, rubidium or cesium. So this type of halides formed by the alkali metal group. Whenever strong base, when treated with hydrogen halide, the formation of metal halides or alkali metal halides along with water means MOH and hydrogen halides, the formation of metal halides along with water. Here M, as we know, is the member of lithium, member of group 1 lithium, sodium, potassium, rubidium and cesium, so on. Enthalpy of formation of halides. Enthalpy of formation of all halides of alkali metal is highly negative. When alkali metal treated with halogen in the form of gases, as we know halogen exists in the form of gaseous, so that formation of metal halides takes place. So balance this equation. More stable is a halide, more negative will be its enthalpy of formation. So write down the points also. More stable is halide, more stable is a halide, more negative will be its enthalpy of formation, will be its enthalpy of formation. Enthalpy of formation. Now, let me discuss the metal halide with the halogen group, means with fluorine and with other halogen group. What happens when alkali metal form the compound with fluorine and when it makes the bond between other than fluorine? So let's we discuss about the fluorides and other halides, means metal fluorides and other halides. So let's we discuss. Fluorides and other halides. Other halides means chloride, bromide, iodide, so on. On moving from lithium to cesium, this is the reasoning questions part. On moving from lithium to cesium, the enthalpy of formation, of fluorides become more and more negative. For other halide, for the other halides, reverse is reverse is formed, that is on moving from lithium to cesium, enthalpy of formation will become less and less negative, less on less negative. So if we see the trends of lithium fluoride, sodium fluoride, potassium fluoride, rubidium fluoride, then cesium fluoride. Enthalpy of formation, as we move top to bottom, enthalpy formation less and less negative. So lithium fluoride to cesium fluoride, the enthalpy of formation more and more negative. Let's we discuss the melting points of halides. Melting points of halides. For same alkali metal, melting point fluoride, then chloride, then bromide, then iodide. Means lithium chloride, lithium chloride, lithium bromide, and lithium iodide. So, and sodium fluoride, sodium chloride, sodium bromide, and sodium iodide. For same alkali metal, melting point form in this. Higher the highest the melting point of lithium chloride, and according to this melting point, lowest the melting point of lithium chloride, and as we move, melting point increases. Fluoride, chloride, bromide, and iodide. So size of anion, fluoride, chloride, bromide, and iodide. So size of anion increases. So that melting point depends on the size of particular molecules. So melting point depends on lattice energy also. Melting point depends on lattice energy. Due to increase in size of anion, increase in size of anion, lattice energy decreases, and hence melting point also decreases. So due to increase in size of anion, lattice energy decreases, and hence melting point also decreases. For same halide anion, this is for same alkali metal. In the next case, for same halide ion, for same halide ion, for same halide ion, lithium, sodium halide, potassium halide, rubidium halide, and cesium halide. So this is smallest in size, so polarizing capacity will be more. Mole polarization means more covalent character, due to Fajan's rule. So in this way, the size of, if we find the size of chlorides, so NaCl, potassium chloride, then rubidium chloride, then cesium chloride, and at last lithium chloride. This will be trend of particular chlorides of group alkali metal. High lattice energy, or decrease in lattice energy from sodium to cesium, and lithium chloride due to polarization power, and generation of or formation of covalent character, and formation of covalent character. So melting points depends on this fact. When the same anion, when same halogen atom and different alkali metal, the trend will be like this, because high lattice energy decreases in lattice energy from sodium to cesium, but lithium chloride here is the exceptional cases, because the size of lithium is small and the size of anion means chloride is larger. So polarization takes place, and due to polarization there is the covalent character increases. So in this way their melting point is very less. Let's we discuss the hydroxides of the group 1 member hydroxides. All forms basic hydroxide of all forms basic hydroxides of MOH type. MOH type. For example, lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxides. The basic character of hydroxide, the basic character of hydroxides increases down the group due to increase in MO bond length. So lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. As we move top to bottom, the bond length increases. So bond length increases, so basic character also increases. If we arrange all the hydroxide, lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and then cesium hydroxide. In this way, top to bottom, the basic character increases. Larger the bond length, smaller the bond dissociation enthalpy, and basic character increases. So basic character increases when we move top to bottom. Basic character increases. Bond length increases, bond dissociation enthalpy decreases, so it can easily release OH ion, and in this way it show the more basic character. So next property is the solubility of hydroxide of alkali metal group. So write down the solubility of hydroxide in water. Means alkali nature. Solubility. Lithium hydroxide is springly soluble in water. Soluble in water. Water due to its high lattice energy. High lattice energy. Whereas others hydroxide are soluble in water. Next, the thermal stability of hydroxide. Thermal stability of hydroxide. All hydroxides are thermally stable. Thermally stable except lithium hydroxide. So lithium hydroxide, when decomposed to form lithium oxide and water. This is the thermal stability trends of hydroxide, and last we discuss the sulfides of alkali metal. Sulfides of alkali metal. Alkali metal form two types of sulfides. First is monosulfides and second is the polysulfides. This is formed by burning the metal in sulfur vapor. Sulfur vapor. Sulfur vapor. Sodium, sulfur, sodium sulfide. This is the example of monosulfides. And polysulfides, it is formed by passing sulfur vapors through a solution of metal in liquid ammonia. Liquid ammonia. Polysulfides have zigzag sulfur chain. Sulfur chain. Na2S6. It is formed like this. 6. 1, 2, 3, 4, 5 and 6. Sulfur and Na plus. Sulfur, 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 sulfur and so in this type polysulfides are formed. High temperature at high temperature reduction of sulfates takes place. At high temperature reduction of sulfates takes place. For example, sodium sulfate when heated with carbon, formation of sodium sulfide and carbon monoxide. So by this points we have completed our property of sulfides of alkali metal, and let's we discuss the anomalous property of lithium, means first member of group 1. What are the anomalous property of lithium? As we see the number of reaction, in this number of reaction lithium shows the property other than the rest of member. What is the reason why lithium, the first member of group 1, show the anomalous property, means property other than the next member? So the anomalous property of lithium. Lithium, the atomic number 3 and the mass number is 6.94. It is first fact is small size, highest polarizing power, highest polarizing power, highest ionization enthalpy, low electropositive, low positive character compared to other member of this group, other metal. So points of difference of lithium with other alkali metals. Points of difference between lithium and other alkali metal. First, all member when treated with water, it will form hydroxide and hydrogen gas. Strong base M, sodium, potassium, rubidium and cesium. Lithium when treated with water, it will form lithium hydroxide and hydrogen gas, and by nature it is weaker base than other member due to small size, high polarizing capacity, high ionization enthalpy, so on. Next, all members when combined with oxygen form either metal peroxide or superoxide or superoxides. But when lithium combined with oxygen to form lithium oxides, which is monoxides. So the diagonal relationship between lithium and magnesium or main group, like period 2 and period 3 or 2 and 3, 1, 2, 13 group number, 14 and 15, lithium, beryllium, boron, carbon and nitrogen. And third period, sodium, magnesium, aluminum, silicon and phosphorus. So diagonally they related: lithium related to magnesium, beryllium related to aluminum, boron resembles with silicon, carbon resembles with phosphorus. So they are the main group. They diagonally show the property like this. So in the next video we will discuss the more other property, in which similar property of lithium magnesium, regarding atomic radius, regarding ionic radius, regarding polarizing power, regarding electronegativity, and points of similarity between lithium and magnesium.